What if everything we think of as modern, our computers, our airplanes, even our robots, was dreamed up thousands of years before it became reality? Picture this: ancient Greek philosophers sketching designs for flying machines, or Egyptian priests describing visions of artificial intelligence in their sacred texts. It sounds impossible, but history is filled with moments where the distant past seems to reach forward, predicting inventions we swear belong only to our time. Today, we're diving into 25 stunning examples of how ancient cultures didn't just imagine the future, they practically blueprinted it. Think about the last time you held a smartphone or watched a drone streak across the sky. These technologies feel like pure 21st century magic, right? But what if I told you the seeds of these ideas were planted centuries, even millennia ago? The ancient world was far more innovative than we often give it credit for. From the mechanical marvels of Alexandria to the prophetic writings of Hindu sages, our ancestors left behind clues that blur the line between myth and science. Some of these predictions were eerily precise, while others feel like cryptic riddles waiting to be decoded. Either way, they force us to ask, were these visions mere coincidence, or did ancient civilizations grasp truths about the universe we're only now rediscovering? This isn't just a trip through history, it's a chance to see the past with fresh eyes. Imagine standing in the shadow of the Great Pyramid, holding a tablet that describes something unmistakably like a helicopter. Or reading a 2,000-year-old poem that perfectly predicts the glow of electric light. These aren't just curiosities, they're whispers from a time when humanity's imagination burned just as bright as ours does today. By the end of this journey, you'll see the ancient world not as a graveyard of forgotten ideas, but as a mirror reflecting our own technological dreams. So let's unravel these mysteries together, one astonishing prediction at a time. The past is about to get a lot more futuristic. Buried beneath the Mediterranean waves for over 2,000 years, a corroded lump of bronze and gears emerged in 1901, clutched in the wreckage of a sunken Roman ship. At first glance, it seemed unremarkable, just another artifact lost to time. But when archaeologists cleaned away the centuries of grime, they uncovered something that shouldn't have existed: the Antikythera Mechanism, an intricate clockwork device so advanced it rewrote our understanding of ancient technology. This wasn't just a tool for telling time. It was a precision-engineered machine capable of predicting the movement of planets, the phases of the moon, even upcoming solar eclipses with uncanny accuracy. A function so complex it wouldn't be matched again until the invention of modern mechanical computers in the 1800s. The genius of this device lies in its miniature cosmos. Tiny interlocking bronze gears, some with teeth cut to exacting mathematical ratios, mimicked the irregular orbits of celestial bodies long before Kepler or Newton formulated the laws governing them. One dial tracked the 4-year cycle of the ancient Olympic Games, while another revealed the timing of lunar eclipses down to the hour. Historians were stunned. How could a civilization without steel or industrial tools craft a mechanism that required knowledge of differential gearing, a concept we wouldn't formalize until the Renaissance? The answer might lie in the writings of Cicero, who described a similar device built by Archimedes, suggesting this wasn't a one-off marvel but part of a lost tradition of ancient engineering. What's even more startling is how familiar its logic feels. The Antikythera Mechanism didn't just calculate, it modeled. Like a prototypical computer, it took inputs, celestial data, and generated outputs, predictions through mechanical algorithms. In that sense, it's a direct ancestor of the devices we use today, proving that the urge to decode the universe through machinery isn't modern at all. It's a human instinct as old as the stars themselves. The real mystery isn't just how they built it, but why this knowledge vanished for millennia, and what other inventions might still be hiding in the ashes of antiquity, waiting to shake our assumptions once more. Deep in the basement of the National Museum of Iraq sits a small clay jar no taller than your hand. Discovered in 1936 near Baghdad, this unassuming artifact, dating back to the Parthian Empire around 2,000 years ago, holds a secret that still sparks controversy among historians. Inside the jar, archaeologists found a copper cylinder housing an iron rod, all sealed with asphalt. At first glance, it could pass for an ancient storage container. But when German scientist Wilhelm Koenig studied it in 1938, he proposed something extraordinary. This was no ordinary pot. It was the Baghdad Battery, a device that may have generated electricity centuries before Volta invented the modern battery in 1800. The design is unsettlingly familiar. The iron rod and copper cylinder, separated by asphalt, a natural insulator, mirror the basic components of a galvanic cell. Pour in an acidic liquid like vinegar or grape juice, and the chemical reaction between the metals could produce around 1 volt of electricity. Experiments with replicas have confirmed it's possible, though the voltage is modest. But here's where the mystery deepens. If this was truly a battery, what was it powering? Some suggest electroplating gilding objects with thin layers of gold, as artisans in Mesopotamia were known for intricate metalwork. Others propose medical applications like mild electric shocks for pain relief, a practice documented in ancient Greek and Roman texts. Yet skeptics argue it might have been merely a sacred storage vessel for scrolls, with the iron and copper serving symbolic rather than electrochemical purposes. What's undeniable is how closely this ancient artifact parallels modern science. The principles behind the Baghdad Battery align with the same electrochemical reactions that power your smartphone today. It's a reminder that the building blocks of technology aren't always modern discoveries, sometimes they're rediscoveries. The real question isn't just whether the Parthians harnessed electricity, but how much knowledge was lost in the shadows between their era and ours. If a simple clay jar could hold such potential, what other fragments of ancient ingenuity are we still overlooking? The waters of Constantinople burned with a fire that refused to be quenched. In the 7th century, as Arab fleets closed in on the Byzantine capital, defenders unleashed a weapon so terrifying it seemed plucked from myth, Greek fire. This liquid flame clung to ships and men alike, blazing even on water, turning the sea itself into an inferno. Historical accounts describe its horror in vivid detail. Jets of fire roaring from bronze tubes mounted on warships, flames leaping from wave to wave as enemy navies dissolved into panic. What made this substance so devastating wasn't just its intensity, but its defiance of nature. Water only spread it, sand might smother it if you could get close enough. For centuries, the formula remained a state secret, guarded so fiercely that its exact composition vanished with the empire that wielded it. Modern historians and chemists have pieced together likely ingredients based on cryptic texts and battlefield reports. The base was almost certainly crude petroleum, distilled into a volatile naphtha-like substance, then mixed with resins to make it sticky and quicklime to ensure it ignited on contact with water. The result, a medieval analog to napalm, centuries before the 20th century weaponized it. The delivery system, pressurized bronze siphons resembling giant blowguns, functioned like primitive flamethrowers, with crews pumping handles to spray streams of fire over 40 feet. One Byzantine chronicle recounts how a single ship armed with these fire tubes routed an entire Saracen fleet, the survivors leaping into the sea to escape the unstoppable blaze. What's most striking isn't just the technology's brutality, but its psychological impact. Greek fire wasn't merely a weapon, it was theater. The Byzantines understood terror as a tactical advantage, using the substance sparingly to magnify its mystique. Enemies whispered that sorcery fueled its flames, and emperors encouraged the rumors. Even the name was a misdirection. Greek fire was likely a later Western label, while Byzantines called it liquid fire or sea fire, reinforcing its otherworldly reputation. Today, we recognize it as a chilling precursor to modern incendiary warfare, proof that humanity's capacity for harnessing destruction isn't a recent development, but an ancient craft refined over millennia. The real legacy of Greek fire isn't just in the ashes it left behind, but in the uncomfortable truth it reveals. Sometimes the past holds shadows of our darkest innovations long before we admit to inventing them. 2,000 years before steam engines powered factories and locomotives, an ingenious inventor in Roman Egypt built a device that should have changed the world. In the 1st century, Hero of Alexandria, a master of mechanics and mathematics, created the eolipile, a spinning sphere powered by nothing but steam. Picture this, a hollow metal ball mounted on a central axis with 2 curved nozzles protruding from its sides. As water inside boiled, jets of steam shot out from the nozzles, causing the entire sphere to whirl with surprising force, a primitive but unmistakable turbine. It wasn't just a curiosity, it was the first recorded instance of steam converting heat into motion, the very principle that would later drive the Industrial Revolution. Hero's writings describe the mechanics with striking precision. The eolipile relied on the same basic physics as modern steam engines. Expanding steam generates kinetic energy. The difference lay in application. While 18th century engineers like James Watt harnessed steam to pump water from mines or propel trains, Hero's invention remained a spectacle, a temple wonder meant to amaze rather than automate. Some historians theorize it might have been used to open temple doors mysteriously, creating divine theater for worshippers. Others suggest it was simply proof of concept, a demonstration of what steam could do in an era lacking the materials or infrastructure to scale it. The ancient world had bronze and craftsmanship, but not the metallurgy to withstand high-pressure steam or the economic incentives to replace cheap slave labor. What makes Hero's device so haunting isn't just its sophistication, but the centuries of untapped potential it represents. The eolipile contained all the necessary ideas for an industrial leap: controlled combustion, rotational force, energy conversion. Yet these insights lay dormant for nearly 1,700 years. When James Watt refined his steam engine in the 1770s, he wasn't reinventing the wheel. He was finally giving Hero's vision the context it needed to transform society. The real mystery isn't why the ancients didn't industrialize, but why it took us so long to realize they'd handed us the blueprint. Hero's steam engine whispers a provocative truth. Sometimes the future arrives in pieces, waiting for the world to catch up to its own ingenuity. Stretching across the arid plains of southern Peru, the Nazca lines form one of archaeology's most baffling puzzles. Etched into the desert floor over 2,000 years ago, these colossal geoglyphs depict everything from intricate geometric shapes to sprawling animals. A hummingbird with wings wider than a football field, a spider with legs perfectly proportioned as if drawn by a master biologist, even a humanoid figure dubbed the astronaut with its eerie, oversized eyes. From ground level, they're little more than shallow grooves in the earth, but from the air, their precision is staggering. How did a culture without flight create designs so vast they can only be fully appreciated from hundreds of feet above? Theories about their purpose range from the pragmatic to the extraordinary. Some scholars argue the lines served as astronomical calendars, aligning with solstices or constellations to track planting seasons. Others suggest they were sacred pathways for rituals, walked by priests to commune with deities. But the most provocative idea, fueled by their aerial perfection, is that the Nazca people possessed knowledge of flight long before the Wright brothers. Ancient hot air balloon experiments using materials available at the time, like woven reeds and open flames, have shown it's technically possible, though no direct evidence survives. Meanwhile, fringe theories point to extraterrestrial influence, citing the impossibility of such precision without advanced technology. Modern technology has only deepened the mystery. Drone surveys and satellite imaging have uncovered hundreds of previously hidden lines, revealing a sprawling, interconnected network that suggests a far more complex system than we once imagined. These new discoveries hint at a purpose beyond mere art or astronomy, perhaps a vast, encoded message or a map of underground water sources, crucial in one of the driest places on Earth. Whatever their true meaning, the Nazca lines stand as a testament to human ingenuity, blurring the line between ancient ritual and what we'd call modern engineering. They challenge us to reconsider not just what our ancestors knew, but how they saw their world from the ground and possibly from the sky. Carved into the stone walls of the Hathor Temple at Dendera, a curious hieroglyph has sparked debates that bridge archaeology and electrical engineering. The so-called Dendera light depicts what appears to be a giant bulbous object, supported by a stem and cradled by a serpentine wavy line, all encased within an elongated chamber resembling a glass enclosure. To modern eyes, the resemblance to a Crookes tube, an early electrical light device, is uncanny. Could this be evidence that ancient Egyptians harnessed electricity, or is it a case of seeing what we want to see in the symbols of the past? Proponents of the ancient electricity theory point to startling details. The bulb shows a filament-like snake extending from a lotus flower base, which they interpret as a filament and socket. The cable trails to a box held by a kneeling figure, suggesting an energy source. Even more compelling are the temple's underground chambers where traces of bitumen, a potential insulator, and copper strips have fueled speculation about primitive wiring. Some researchers draw parallels to the Baghdad Battery, proposing these elements formed a rudimentary power system for illumination, explaining why Egyptian tombs lack soot from torches despite intricate artwork requiring light to create. But skeptics offer a very different reading. Egyptologists identify the scene as a symbolic representation of a cosmic serpent emerging from a lotus, part of a well-documented creation myth involving the god Harsamtis. The bulb mirrors the shape of ceremonial vessels used in rituals, while the serpent symbolizes divine energy, not electricity. As for the lack of soot, mirrors strategically placed to reflect sunlight or oil lamps with carefully designed chimneys could explain the pristine walls. The real irony: the Crookes tube theory gained traction in the 1940s precisely when such technology was fresh in the public imagination, suggesting our own modern lens might be distorting ancient intent. The Dendera carving's power lies in its ambiguity. It challenges us to confront how easily we project our world onto the past, while leaving room for the possibility that some knowledge truly was lost to time. Whether it's a sacred symbol or a schematic, one thing is clear: the ancients encoded their understanding of energy in ways we're still deciphering. Perhaps the truth isn't binary, not purely myth nor outright technology, but a reminder that the line between the two was always thinner than we assume. The Pantheon still stands untouched after nearly 2,000 years, its massive dome defying time, weather, and even earthquakes, while modern concrete structures crumble after mere decades. The secret lies in a recipe lost for centuries: Roman concrete, a material so resilient it doesn't just endure damage, it repairs itself. Recent studies have revealed that the key ingredient wasn't some exotic alchemy, but volcanic ash from the region of Pozzuoli. When mixed with lime and seawater, this ash triggered a chemical reaction that created crystals within the concrete, filling cracks as they formed. It's a process modern scientists call autogenous healing, and it's something today's concrete simply can't replicate. What makes Roman concrete even more remarkable is how it strengthens over time. While our modern versions degrade when exposed to salt water, a major problem for coastal cities, the Roman mixture thrived in it. Marine structures like the harbor at Caesarea Maritima in Israel remain intact after 2 millennia, submerged in the Mediterranean yet untouched by erosion. Modern engineers have spent years reverse engineering this ancient marvel, and what they've discovered challenges everything we thought we knew about construction. The Romans didn't just build for their era, they built for eternity using chemistry we're only now beginning to understand. The implications for sustainability are staggering. Contemporary concrete production accounts for nearly 8% of global carbon emissions, partly because it relies on Portland cement, a material that requires superheating limestone at enormous energy costs. Roman concrete, by contrast, used less lime and cured at lower temperatures, making it far greener. Laboratories are now racing to recreate the formula, with one team at the University of Utah successfully mimicking the self-healing properties by adding volcanic rock to modern mixes. If perfected, this ancient technology could revolutionize seawalls, bridges, and even nuclear waste storage, structures where longevity isn't just convenient but critical. Yet the real lesson here isn't just about materials, it's about mindset. The Romans weren't just constructing buildings, they were crafting legacies, prioritizing durability over speed and cost. In an age where disposable architecture dominates, their concrete whispers a provocative question. What if the most advanced technology isn't always the newest? Sometimes the future we're searching for has been buried in the past all along, waiting for us to rediscover its wisdom. The Pantheon's unbroken dome isn't just a monument, it's a challenge, daring us to build not just for now but for the ages. In the year 138, a thunderous roar shook the halls of China's Han Dynasty court. Officials scrambled as word arrived of an earthquake in a province hundreds of miles away, yet no messengers had raced in with the news. Instead, the warning came from an ornate bronze vessel in the palace, where a single dragon's mouth had clattered open, dropping a metal ball into the waiting cup of a carved toad below. This was Zhang Heng's seismoscope, an invention so ahead of its time that modern engineers wouldn't replicate its sensitivity until the 19th century. The device stood 8 feet tall, its surface adorned with 8 sinuous dragons, each holding a ball above corresponding toads. When an earthquake's tremors rippled through the earth, an ingenious internal pendulum swung toward the quake's origin, triggering only one dragon to release its payload. The direction of the fallen ball revealed the epicenter's location, an uncanny feat of mechanical intuition 1800 years before Richter scales. The brilliance of Zhang Heng's design lay in its elegant simplicity. Unlike modern seismographs that record vibrations electronically, his seismoscope functioned purely through kinetic energy. Historians believe a central inverted pendulum swayed within the vessel, connected to delicate levers that acted like a mechanical switch. Only seismic waves arriving from a specific angle would trip the precise mechanism needed to dislodge a single ball. Even more remarkably, contemporary accounts suggest it detected quakes too faint for humans to feel, a sensitivity that baffles researchers today, given the era's limited understanding of seismic waves. Some speculate the bronze resonance amplified subtle vibrations, while others propose hidden mercury channels acted as liquid stabilizers. The original device vanished centuries ago, leaving modern reconstructions to test these theories with mixed success. What makes this ancient detector so startlingly modern isn't just its accuracy, but its underlying philosophy. Zhang Heng didn't view earthquakes as acts of gods, but as natural phenomena that could be measured and anticipated, a radical idea for 2nd century China. His design shares DNA with today's seismometers, which also rely on suspended masses to detect ground motion, though now enhanced by digital sensors and satellite networks. Yet in one respect, the ancient model surpasses the modern, its instant visual communication. While scientists today must interpret squiggly lines on a seismogram, the seismoscope's falling ball provided immediate, unambiguous data, a user-friendly interface we've only recently re-embraced with smartphone earthquake alerts. Perhaps the most poignant detail lies in the dragons themselves. These weren't arbitrary decorations, they aligned with the 8 cardinal directions of Chinese cosmology, embedding the device within a worldview where nature and technology intertwined seamlessly. Modern seismology may have traded bronze artistry for microchips, but the core challenge remains unchanged: how to listen to the Earth's whispers before they become roars. Zhang Heng's seismoscope stands as a testament to humanity's timeless quest to predict the unpredictable, a reminder that the line between ancient ingenuity and modern science is often thinner than we think. High above the jungles of Mesoamerica, the Maya tracked celestial events with an accuracy that still leaves astronomers speechless. Without telescopes or advanced optics, they calculated the solar year to 365.242 days, just 17 seconds shorter than our modern measurement. Their Venus tables, etched into the Dresden Codex, predicted the planet's 584-day cycle with an error margin of just 2 hours over 500 years. But perhaps most astonishing is their eclipse calendar, a complex web of calculations that pinpointed lunar and solar eclipses centuries in advance by recognizing patterns invisible without precise, generations-long record-keeping. At the heart of this precision lay mathematics far ahead of its time. While Europe languished in the Dark Ages, Mayan scholars operated with a base 20 numbering system that included the concept of zero, a leap in abstract thinking many cultures wouldn't achieve for centuries. Their long count calendar didn't just mark days, it synchronized multiple cosmic cycles from the agricultural year to the sacred 260-day Tzolk'in, creating a temporal lattice that wove together human and celestial rhythms. The famed 2012 phenomenon, a simple reset in this vast cycle, misinterpreted as apocalyptic prophecy when in reality, it showcased their grasp of time's cyclical nature, an idea modern physics now echoes in theories of cosmic recurrence. Modern planetarium software owes an unexpected debt to these ancient skywatchers. Algorithms that predict eclipses or model planetary motion today rely on the same pattern recognition the Maya perfected, just processed by silicon instead of stone observatories. At Chichen Itza, the El Caracol Observatory's narrow windows align with Venus's extreme positions on the horizon, proving their observations weren't merely theoretical. Meanwhile, Temple Roman 4 at Tikal Summit frames the Milky Way during the summer solstice, turning architecture into a celestial compass. These structures weren't just buildings, they were analog computers encoding astronomical data in stone angles and shadow play. What truly sets the Maya apart was their synthesis of science and spirituality. They didn't just track planets, they believed celestial bodies were gods whose movements influenced earthly events. This duality, combining meticulous observation with cosmic storytelling, reveals a sophistication modern science often lacks. Where we separate astronomy from mythology, the Maya saw them as inseparable, reminding us that the coldest calculations gain meaning when connected to human wonder. Their legacy isn't just in the accuracy of their charts, but in their vision of a universe where numbers and stars alike tell stories. An idea any modern astrophysicist might recognize when gazing at the night sky, humbled by its infinite equations. Hidden within the epic Sanskrit texts of ancient India lie descriptions so precise, they read like technical manuals for machines that shouldn't exist for thousands of years. The Mahabharata and Rigveda speak of Vimanas, mystical flying chariots adorned with glowing metals, capable of soaring across continents and even into space. Some accounts detail speeds that could circle the globe multiple times in a day, while others describe aerial battles with weapons eerily reminiscent of modern missiles. One passage in the Samarangana Sutradhara even breaks down the mechanics: mercury-powered engines, rotating fans for lift, and insulated cabins to protect pilots from the violent winds of high-altitude flight. The details are so specific that when British archaeologist David Davenport stumbled upon them in the 1960s, he famously asked, "Were the ancients documenting myth or memory?" Scholars remain deeply divided on how to interpret these texts. Traditionalists argue that Vimanas are purely symbolic celestial metaphors for spiritual ascension, much like the fiery chariot of the prophet Elijah in the Bible. The Mercury propulsion, allegory for Kundalini energy rising through the body's chakras, but a growing faction of researchers point to unsettling consistencies with real aerodynamics. The Vaimanika Shastra, a controversial early 20th century text claiming to be based on lost manuscripts, describes aircraft with features like ghost mirrors for invisibility and solar-powered crystals for energy concepts that feel less like mythology and more like speculative engineering. Even more striking are the accounts of aerial warfare in the Mahabharata, where flaming arrows leave entire cities as lifeless as fallen birds, paralleling modern depictions of nuclear fallout. The smoking gun might lie in the gaps of history. India's iron pillar of Delhi, standing rust-free for over 16 centuries, hints at metallurgical knowledge we've only recently rediscovered through nanotechnology. Could Vimanas represent a lost tradition of experimentation with materials and forces we assume were beyond ancient reach? Aerospace engineer Jonathan Colmer notes that Mercury's unique properties, its ability to conduct electricity and create plasma under certain conditions, align disturbingly well with theoretical propulsion systems NASA has explored for advanced spacecraft. Meanwhile, carvings at the 6th century Shiva temple in Ellora depict figures inside what appear to be cockpit-like structures, their hands gripping controls as flames erupt from the base, images that fuel speculation about cultural memories of real technology. Perhaps the truth lies somewhere between poetry and physics. The Vimana texts emerge from a civilization that saw no divide between science and the sacred, where the mechanics of flight could be as divine as the destinations. Whether these accounts document literal machines or the outer edges of human imagination, they challenge us to reconsider what advanced truly means. After all, every myth holds a kernel of truth, and sometimes that kernel takes flight in ways we're only beginning to understand. Archimedes' most audacious weapon wasn't forged from steel or powered by gunpowder, it harnessed the sun itself. According to ancient historians like Lucian and Galen, during the Roman siege of Syracuse in 212 B.C., the brilliant mathematician devised a terrifying array of bronze mirrors mounted on the city walls. When enemy ships ventured too close, these mirrors allegedly focused sunlight into a searing beam, setting vessels ablaze from 300 feet away. For centuries, scholars dismissed the story as legend until a pivotal experiment in 1973. Greek engineer Ioannis Sakas arranged 70 copper-coated mirrors, each the size of a classroom door, targeting a plywood mock-up of a Roman warship. Within minutes, flames erupted, proving the concept worked under ideal conditions. But was this really Archimedes' doing, or just a dramatic reconstruction? The physics behind the death ray reveal both its potential and its limitations. Modern calculations show that to ignite damp, pitch-covered ship timbers, the mirrors would need to concentrate sunlight to roughly 500 degrees Fahrenheit across a 3-foot spot, a feat requiring near-perfect alignment of hundreds of polished surfaces. MIT students recreated the experiment in 2005 with mixed results. While they generated smoke and charring, sustained ignition proved elusive without ideal weather and stationary targets. Critics argue that ancient Syracuse's bustling harbor, with bobbing ships and frequent cloud cover, would have made the weapon impractical in real combat. Yet supporters counter that Archimedes, who already understood parabolic reflectors through his work on burning glasses, might have employed a more sophisticated array than simple flat mirrors. Some texts hint at hexagonal panels arranged like a honeycomb, a design that could compensate for individual aiming errors through collective focus. Perhaps the most compelling evidence lies not in whether it worked once, but why the story persisted. Multiple independent accounts from antiquity describe similar devices across the Mediterranean, suggesting the concept had wider currency. The Byzantines later used polished shields to signal and blind enemies, while Leonardo da Vinci sketched solar concentrators for industrial heating centuries later. What makes Archimedes' version stand out is its scale and intent, not just a tool, but a weaponized application of pure mathematics. Even if its battlefield efficacy was exaggerated, the death ray symbolizes a pivotal moment when theoretical science collided with military pragmatism. Today, the principle lives on in modern concentrated solar power plants, where mirrors the size of houses focus sunlight to drive turbines, proof that the line between ancient wonder and cutting-edge technology is often just a matter of scale and persistence. The real lesson of Archimedes' mirrors isn't whether they burned ships, but how they illuminate humanity's endless ingenuity in turning even sunlight into a tool or a weapon. Buried in the sands of ancient Thebes, a 3,000-year-old artifact rewrote medical history, not a scroll or a scalpel, but a toe. Not just any toe either. This was the Cairo toe, a meticulously crafted prosthetic made of leather and wood, discovered still strapped to the foot of a mummy in 2000. What stunned researchers wasn't just its age, dating to between 950 and 710 BCE, but its sophistication. The toe wasn't merely cosmetic, it showed signs of wear and adjustments, suggesting its owner relied on it for balance and mobility. Modern biomechanical analysis revealed something even more startling. The design followed principles we now recognize as essential for comfortable prosthetics: flexible joints, contoured fit, and weight distribution. This wasn't a ritual object, it was functional engineering born from an era we often assume had no grasp of practical medicine. The Cairo toe wasn't alone. Across Egypt, archaeologists have unearthed prosthetic fingers, ears, and even an impeccably preserved artificial leg from the Roman period. Each one defies expectations. The Greville-Chester great toe, carved from cartonnage, a mixture of linen, glue, and plaster, boasts a hinge that mimics natural movement. Then there's the Capua leg, a bronze and wood replacement found in Italy but crafted with Egyptian techniques, complete with a locking mechanism for stability during walking. These weren't crude attempts, they were solutions born from careful observation of anatomy and a deep understanding of materials. Egyptian medical texts like the Edwin Smith Papyrus, which detail surgical techniques for trauma, suggest this culture viewed bodily restoration not as magic but as a solvable problem. What's most revealing is how these ancient designs parallel modern prosthetics. Today's carbon fiber limbs prioritize lightweight durability and articulation, the same principles guiding that leather and wood toe 3 millennia ago. The Egyptians even accounted for hygiene. Some prosthetics featured ventilated materials to prevent skin irritation, a concern modern engineers still grapple with. Researchers at Manchester University tested replicas using pressure-sensitive mats and found the weight distribution so effective it could rival early 20th century designs. This level of innovation didn't emerge in a vacuum. Egypt's cultural reverence for bodily wholeness, essential for the afterlife, drove them to refine functional replacements, blending spiritual necessity with biomechanical insight. The real breakthrough here isn't just the technology itself, but the philosophy behind it. These artisans didn't see disability as a fixed state, they saw it as a challenge to engineer around. That mindset, the belief that the human body can be augmented and restored, is the cornerstone of modern biomedical engineering. From myoelectric arms to 3D printed joints, we're still walking the path those ancient craftsmen began. The difference: they had no textbooks, no polymers, no microscopes, just observation, creativity, and an unwavering determination to rebuild what was lost. Their legacy lingers in every lab today, where scientists push the boundaries of what's possible, proving that sometimes the future of medicine isn't just about moving forward, it's about rediscovering the wisdom already buried in the past. Imagine walking into an ancient Greek temple and witnessing a miracle: statues that pour wine without human touch, mechanical birds that sing with the flutter of bronze wings, or even an entire theater where miniature robotic actors perform a tragedy without a single puppeteer. This wasn't fantasy, it was the work of engineers like Hero of Alexandria, whose automata, self-operating machines, were the closest thing the ancient world had to robots. In the 1st century CE, Hero designed devices powered by steam, water, and intricate systems of weights and pulleys, creating illusions of life that blurred the line between divine magic and mechanical genius. His most famous invention, the automatic theater, was a portable stage where tiny figures acted out an entire play, their movements timed by rotating drums and strings, an ancient precursor to the programmable machines we take for granted today. The technology behind these marvels was shockingly sophisticated. Hero's wind-powered organ used a rotating wheel to pump air into pipes, generating music without human intervention, a principle later adapted in modern player pianos. Another device, the automatic servant, stood at temple entrances, dispensing holy water when visitors dropped a coin into a slot. The mechanism, a clever counterweight system where the coin's weight tilted a lever, releasing a measured amount of liquid before resetting itself. It wasn't just functional, it was interactive, a 2,000-year-old vending machine designed to inspire awe and devotion. These creations weren't toys or curiosities. They were demonstrations of an emerging understanding of automation, proof that the ancients grasped concepts we associate with robotics long before electricity or microchips. What's even more striking are the parallels to modern AI-driven automata. Hero's machines relied on if-then logic centuries before computer programming formalized the concept. Take his automatic door system for temples. When priests lit a fire on the altar, heated air expanded in a hidden chamber, displacing water that turned pulleys to swing the doors open. Replace the fire with a motion sensor and the pulleys with servomotors, and you've got the same basic principle behind today's automated entrances. The difference lies in execution, not intent. Even the theatrical automata, with their pre-programmed sequences, share DNA with modern animatronics. Think Disney's lifelike robots or Boston Dynamics dancing machines, all descendants of Hero's rotating drum controllers. Yet the most fascinating aspect isn't the mechanics, it's the philosophy. The Greeks didn't view these machines as mere tools, but as embodiments of the divine. Temple automata were often designed to evoke epiphanies, creating moments where worshippers couldn't distinguish between the hand of a god and the gears of a machine. In that sense, they predate our own debates about artificial intelligence and consciousness. When a robotic priestess in a Delphic shrine spoke oracles through hidden pipes, was it so different from today's AI chatbots that mimic human conversation? Both challenge us to ask where the line between simulation and sentience truly lies. Hero's legacy lingers in every automated system around us, from factory robots to smart home devices. But perhaps his greatest lesson isn't technical but existential. These ancient automata remind us that the urge to create life from mechanics isn't a modern obsession, it's a timeless human impulse. The Greeks may not have had silicon or software, but they understood something fundamental. Technology, at its best, doesn't just serve us, it astonishes us, mirroring our own creativity back in ways that still feel like magic. High in the Andes Mountains, the walls of Sacsayhuaman stand as a silent challenge to everything we assume about ancient construction. These aren't just stones, they're puzzles. Massive blocks of andesite, some weighing over 100 tons, fit together so precisely you can't slide a razor blade between them. No mortar, no gaps. Just a seamless, earthquake-resistant jigsaw that's endured for over 600 years. The mystery isn't just how the Inca achieved this precision without metal tools or the wheel. It's why their later Spanish conquerors, armed with Renaissance technology, couldn't replicate it. When colonial chronicler Pedro Cieza de Leon first saw these walls in the 1550s, he wrote they were built not by men but by demons, because no human hand should have been capable of such perfection. The closer you look, the more baffling it becomes. Unlike Egypt's flat-surfaced pyramids, Inca masonry features complex interlocking shapes, convex bumps nesting into concave hollows, corners with 12-angled joints, even stones that curve like melted wax to match their neighbors. At Ollantaytambo, one block has 72 distinct edges, each cut to millimeter precision. Modern engineers using laser scanning have discovered something even stranger. The stones aren't just tightly fitted, they're slightly flexible. Tiny undulations in the surfaces allow the walls to shift during earthquakes before settling back into place, a feature contemporary architects are only now incorporating into seismic-proof designs. This wasn't crude hammering, it was stone engineering on a molecular level. So how did they do it? The Quechua oral tradition speaks of llama's blood mixed with herbs softening stone, a recipe lost during Spanish colonization. Geologists note that certain Andean plants contain oxalic acid, which could chemically weaken rock surfaces for shaping. Others propose the Inca used bronze tools with abrasive sand to slowly grind fittings, a plausible but agonizingly slow process for projects involving thousands of blocks. Then there's the controversial sunstone theory. Ancient texts mention concave mirrors or lenses that concentrated sunlight to melt or soften stone, similar to Archimedes' legendary death ray. Experiments with polished bronze dishes have shown temperatures exceeding 2000 degrees Fahrenheit are possible hot enough to vitrify rock surfaces into glassy, precision edges. The real shock comes when you compare Inca techniques to modern technology. Today's laser-cut stone cladding for high-end architecture achieves similar seamless joints but requires computer-guided machinery. The Inca had no written language, no pulleys, no iron chisels, yet their walls mock our assumptions about progress. At Coricancha, Cusco's Sun Temple, Spanish colonists built a convent atop Inca foundations. After countless earthquakes, the Spanish walls crumbled repeatedly while the Inca base remained untouched. The lesson is humbling. Sometimes ancient solutions outpace modern ones. Perhaps the answer isn't lost tools, but lost knowledge. The Inca didn't view stone as inert material. They believed it held life force or kamak. Master masons might have listened to rocks, selecting blocks that naturally complemented each other like musical harmonies. This spiritual approach, combined with empirical observation, could explain their otherworldly precision. In the end, their walls aren't just relics, they're mirrors, reflecting back our own cultural arrogance about what technology should look like. The laser may be new, but the quest for perfection is ancient. In the dusty ruins of ancient Babylon, a cracked clay tablet sat unnoticed for decades among thousands of others in the British Museum's collection. Then in 2017, mathematician Dr. Daniel Mansfield made a discovery that rewrote mathematical history. This wasn't just another inventory list or royal decree. Tablet Plimpton 322 contained the world's oldest trigonometric table, carved in cuneiform nearly 4,000 years ago. What makes this tablet extraordinary isn't just its age, but its sophistication. While Greek astronomer Hipparchus is often credited with inventing trigonometry around 150 B.C., the Babylonians had perfected a far more elegant system over a millennium earlier. Their approach didn't use angles or degrees like modern trigonometry. Instead, it relied on ratios between the sides of right triangles, a method so efficient that Mansfield's team found it outperforms contemporary techniques for certain calculations. The tablet's 15 rows of perfectly preserved numbers form what mathematicians call a Pythagorean triple table, precise measurements that could have been used to survey land, construct towering ziggurats, or track celestial movements. Each row describes a right triangle with whole number sides, like 3, 4, 5, or 5, 12, 13, but scaled up to far larger and more complex proportions than simple textbook examples. One entry details a triangle with sides measuring 1296, 6905, and 7,089 units, numbers so precise they suggest an understanding of mathematical relationships we'd only formally rediscover in the Renaissance. Unlike Greek trigonometry, which relied on cumbersome angle measurements, the Babylonian system used base 60 fractions, the same system that gives us 60-minute hours, to create what Mansfield describes as trigonometry stripped down to its raw, beautiful essentials. But why would ancient scribes need such advanced math? The answer might lie in Babylon's architectural marvels. The city's famed Ishtar Gate, with its precise 45-degree angles and perfectly proportioned tiers, would have required exact geometric calculations. Even more compelling is the tablet's potential use in astronomy. Babylonian star catalogues tracked planetary motions with astonishing accuracy. They knew Venus repeats its cycle every 584 days and could predict lunar eclipses centuries in advance. Such feats demand precise tools for measuring distances between celestial objects. The tablet's ratios could have functioned like an ancient GPS for the heavens, allowing priests to map the night sky using pure mathematics rather than observational guesswork. What's truly humbling is how differently the Babylonians approached problem-solving compared to later civilizations. Where Greeks saw circles and angles, Babylonians thought in ratios and reciprocals, a perspective that feels oddly modern. Today's computer graphics and engineering simulations often use similar ratio-based math because it's faster and less prone to rounding errors than angle-based systems. In that sense, Plimpton 322 isn't just a relic. It's a 4,000-year-old lesson in mathematical elegance, proving that sometimes the most advanced solutions aren't the newest, but the ones we forgot along the way. The tablet's cracked surface holds more than numbers. It whispers a truth that reshapes our timeline of human genius, that the seeds of calculus, physics, and even space travel might have been planted in the Fertile Crescent millennia before we dared to dream them. Held in the dim light of a museum case, the Lycurgus cup looks unremarkable until you shift the angle. Suddenly, this 4th-century Roman drinking vessel transforms from dull green to a glowing ruby red, as if filled with liquid fire. For centuries, this optical magic baffled historians. Then, in the 1990s, electron microscopy revealed the secret. The glass contains billions of gold and silver particles, each smaller than a grain of sand, precisely engineered at the nanoscale to manipulate light. This isn't just artistry, it's ancient nanotechnology, a level of material science we assumed was impossible until the late 20th century. The cup's creators didn't just stumble upon this effect. Analysis shows the gold particles measure about 50 nanometers in diameter, the exact size needed to scatter light in a phenomenon we now call surface plasmon resonance. Silver particles added in careful ratios tweak the color balance. To achieve this, Roman artisans had to grind precious metals to dust, suspend them in molten glass without clumping, then anneal the mixture at controlled temperatures. It's a process requiring knowledge of chemistry and physics that textbooks claimed didn't exist before the invention of electron microscopes. Modern labs replicating the technique found even slight deviations, particles 10 nanometers larger or a few degrees hotter, result in murky brown glass instead of that mesmerizing color shift. But the Lycurgus cup isn't alone. Across the ancient world, artifacts display similarly impossible precision. Damascus steel blades, famed for their flexibility and razor-sharp edges, contained carbon nanotubes, microscopic structures first observed in the 1950s. Chinese Han Dynasty bronzes from 2,000 years ago show evidence of chromium oxide coatings to prevent rust, a technique only patented in modern times. Even Mayan blue paint, which retains its vivid hue after centuries in humid jungles, owes its longevity to nanostructured clay particles that bind indigo dye at a molecular level. What ties these discoveries together is intent. These weren't accidental quirks of chemistry, they were deliberate innovations. Roman glassmakers likely noticed that gold-spiked glass changed color when heated differently, then refined the method through trial and error. Damascus swordsmiths may have unknowingly harnessed carbon nanotube formation by folding and reforging steel with specific ores. These artisans operated without microscopes, but their empirical observations led them to manipulate matter at scales invisible to the naked eye. Today, we're rediscovering their principles in cutting-edge applications. The same plasmonic effect that gives the Lycurgus cup its shimmer is now used in medical diagnostics, where gold nanoparticles detect cancer biomarkers in blood samples. Chromium coatings protect spacecraft just as they once preserved ancient bronzes, and researchers studying Damascus steel's nanostructures are developing new alloys for everything from surgical tools to jet engines. The irony is rich. Our most advanced materials science often circles back to solutions our ancestors pioneered through patience and keen observation. The real lesson here isn't just about lost techniques, it's about redefining what advanced means. Nanotechnology isn't a modern invention, it's a rediscovery. Those Roman glassmakers couldn't articulate quantum physics, but they mastered its effects through craftsmanship. Their work challenges the linear narrative of scientific progress, suggesting instead that innovation is a spiral, where ancient insights occasionally outpace our own until we're ready to understand them. The Lycurgus cup, glowing across 16 centuries, is more than a relic, it's a beacon, reminding us that the smallest details often hold the biggest secrets. Long before telescopes or quantum physics, Hindu sages described time not as a straight line, but as an endless cosmic wheel, a concept that sends chills down modern physicists' spines. The ancient Puranas divide existence into 4 repeating epochs called yugas, each lasting hundreds of thousands of years, cycling from golden ages of enlightenment to dark eras of ignorance before beginning anew. What's startling isn't just the vast timescales far exceeding early Western notions of history, but how closely these cycles mirror cutting-edge theories about the universe's fate. The Hindu Kalpa, a single day of Brahma spanning 4.32 billion years, aligns unnervingly with current estimates of Earth's age. Even more jarring is the description of cosmic dissolution, or pralaya, where the universe contracts into a singular point before re-emerging, a process that echoes the Big Crunch hypothesis, where gravitational collapse reverses the Big Bang. Dig deeper into the Sanskrit texts and the parallels grow more surreal. The Vishnu Purana describes infinite parallel worlds, each with its own Brahma-governing creation, a multiverse theory millennia before Everett's quantum mechanics. The Mahabharata even hints at time dilation, stating celestial years differ from earthly ones, much like Einstein's relativity predicts clocks tick slower near massive objects. Modern cosmologists grapple with cyclic universe models where dark energy might one day flip to dark matter, triggering a new Big Bang. Yet this idea feels eerily familiar to anyone who's read the Bhagavata Purana's verses on cosmic breathing, where universes expand and contract like lungs. The real mystery isn't whether ancient seers predicted modern physics. It's how they conceptualized such vast ideas without mathematical tools. Unlike Greek or Babylonian astronomers who relied on geometric calculations, Hindu cosmology emerged from meditation and metaphysics. Rishis spoke of seeing cosmic truths in heightened states of consciousness, describing realities later quantified by equations. Take the concept of Maya, the illusion separating humans from perceiving deeper universal truths, a notion that resonates with modern holographic principle theories, where our three-dimensional reality might be a projection from a two-dimensional boundary. Skeptics argue these are coincidences, that vague, poetic language can be retrofitted to match science, but the specificity defies easy dismissal. The Linga Purana calculates Earth's diameter at 7,900 miles, only 2% off the actual value. The Aitareya Brahmana describes the Sun as stationary while planets orbit, predating Copernicus by 3,000 years. Even the ratio of atomic particles in Hindu texts 9 outer electrons to 1 inner core, mirrors the structure of our solar system. Perhaps the most humbling lesson lies in the yugas themselves. We live in Kali Yuga, the darkest age according to the cycle, yet the texts promise another golden era will dawn. It's a cosmic perspective that tempers our modern arrogance, reminding us that civilizations rise and fall, but knowledge might be more eternal than we realize. Whether through divine revelation or lost scientific traditions, these ancient models challenge us to wonder, are we discovering the universe's secrets or just remembering them? Legend claims Viking ships could find their way even when the sun vanished behind thick clouds, not with compasses, but with glowing stones that pierced the gloom. These weren't magical artifacts, but perhaps something even more remarkable: naturally occurring calcite crystals known as sunstones, capable of detecting sunlight invisible to the naked eye. Imagine a mariner holding a translucent piece of Iceland spar up to the overcast sky. As they rotate the crystal, sudden flashes of brightness reveal the sun's hidden position, thanks to a property called birefringence, where light splits into two beams, creating contrasting patterns that betray the sun's location. It's a trick modern optics now understands as polarization, the same principle behind polarized sunglasses or airplane navigation systems. The first hard evidence emerged in 2013, when archaeologists excavating a 16th century English shipwreck found a calcite crystal buried near navigational tools. Though the vessel postdated the Viking Age by centuries, the discovery confirmed Europeans used such stones long after magnetic compasses became common. Even more compelling is a study by Hungarian researchers who sailed a replica Viking ship using only a sunstone on overcast days and successfully navigated within 1% of their target coordinates. The crystal's effectiveness hinges on atmospheric physics. Even when clouds scatter sunlight, some polarized light penetrates, vibrating in predictable patterns. Calcite acts like a prism for these hidden clues, turning diffuse skylight into a directional compass. But skeptics raise valid questions. No Viking-era sunstone has been definitively identified in Scandinavia, though calcite deposits exist in Iceland, fittingly a key Viking trading hub. Some argue oral sagas describing sunstones might have referenced other minerals like cordierite, which also polarizes light. Yet the clincher may lie in a 14th century Icelandic manuscript detailing how to locate the sun when stars are hidden, instructing sailors to use a solar stone to check the sky's brightness. Combine this with the fact that Viking routes stretched from Newfoundland to Constantinople, often under northern latitudes where overcast days dominate, and the theory gains weight. These weren't primitive tools, they were sophisticated adaptations to environmental challenges. What makes sunstones revolutionary isn't just their utility, but the insight they reveal about Viking ingenuity. While medieval Europe relied on crude magnetic compasses that faltered near the poles, Norse navigators might have exploited the physics of light itself. Modern polarizing filters in cameras and LCD screens operate on identical principles, filtering scattered light to enhance clarity. Even today's pilots train with polarization-based instruments for emergencies when GPS fails. The Vikings didn't just endure harsh conditions, they decoded nature's hidden signals to master them. Whether calcite, cordierite, or another mineral, these stones crystallize a truth. Sometimes the most advanced technology isn't invented but discovered, lying in plain sight for those who know how to look. The carvings at Dendra's Hathor Temple continue to ignite fierce debate not just among archaeologists, but engineers and physicists who have taken the so-called Egyptian lightbulb theory from speculation to laboratory testing. At the heart of the controversy is one striking image: a bulb-like object encasing a serpentine filament, connected by a cable to what appears to be a power source held by a kneeling figure. To some, this resembles a Crookes tube, an early electrical light device from the 19th century. But could it really depict ancient technology, or are we projecting modern ideas onto sacred symbolism? Recent experiments have pushed the boundaries of plausibility. A team from the University of Kassel constructed a replica based on the carvings, using only materials available to ancient Egyptians: copper, bronze, and an electrolyte like grape juice. Their version produced a faint glow, supporting claims that the design could function as a primitive lamp. Meanwhile, researchers in Prague focused on the temple's underground crypts, where traces of bitumen, a natural insulator, and unusual copper residues hinted at possible electrochemical activity. Even more provocative are the temple's ceiling carvings, which show what some interpret as insulated cables snaking toward hidden chambers, details mainstream Egyptology dismisses as symbolic sun barks or serpent deities. Yet Orthodox scholars counter with compelling evidence of their own. The filament closely resembles the hieroglyph for Jed, a pillar symbolizing stability, while the bulb matches the shape of ceremonial vessels used in rituals honoring the sky goddess Nut. The entire scene, they argue, depicts the nightly journey of the sun god Ra through the underworld, with the serpent representing his regenerative power, not electricity. As for the temple's pristine, soot-free walls, mirrors of polished copper could have redirected sunlight deep into corridors, a technique demonstrated in a 2019 study where reflective surfaces illuminated windowless chambers with 95% efficiency. What makes this debate so gripping isn't just the clash of interpretations, it's the underlying question about how knowledge is preserved. If the carvings do encode technical knowledge, it would mean the Egyptians possessed an understanding of energy transmission that vanished for millennia. But even if mainstream Egyptology is right, the precision of these symbols reveals something equally profound. A culture that blurred the line between the physical and metaphysical, where light wasn't just a tool but a divine force. The Dendera carvings challenge us to consider whether our categories of technology and myth might be far more fluid than we assume. Perhaps the truth lies in synthesis. The temple's artists may not have been documenting literal light bulbs, but channeling observations of natural phenomena, bioluminescent algae in the Nile, or static electricity from desert winds into sacred art. After all, the same civilization that tracked stars with pinpoint accuracy also saw them as celestial gods. In that light, Dendera's bulb becomes a bridge between worlds, part blueprint, part prayer, and a reminder that the spark of innovation often flickers where science and spirituality meet. 2,400 years ago, a Greek philosopher named Democritus sat by the Aegean Sea, breaking a loaf of bread into smaller and smaller pieces until he couldn't divide it further. This simple act led to a revolutionary idea that all matter consists of tiny, indivisible particles he called atomos, meaning uncuttable. While his contemporaries like Aristotle believed in continuous matter, Democritus envisioned a universe built from these invisible building blocks, moving through void space, combining and recombining to create everything from rocks to human flesh. His theory wasn't just a lucky guess, it was a startlingly prescient framework that wouldn't be proven scientifically until the early 19th century. What's remarkable is how closely Democritus' speculations mirror modern atomic theory. He proposed that atoms differed in shape and size, some smooth, others hooked or jagged, explaining why substances like water flowed while iron remained solid. Today, we know atoms combine based on electron configurations and bond angles, but the underlying principle is eerily similar. Even more astonishing, he suggested atoms were eternal and unchangeable, aligning with the law of conservation of mass. Democritus even theorized about the existence of multiple worlds, each formed by random atomic collisions, a concept that parallels modern multiverse hypotheses in quantum physics. Yet for centuries, his ideas were dismissed as fringe philosophy. Aristotle's opposing view, that matter was infinitely divisible, dominated Western thought, reinforced by medieval scholars who integrated it into Christian theology. The Catholic Church's adoption of Aristotelian physics made atomism heretical, delaying its acceptance until the scientific revolution. When Renaissance thinkers like Galileo and Newton began questioning classical doctrines, they cautiously revived atomic theory, though proof remained elusive. It wasn't until John Dalton's experiments with chemical ratios in the early 1800s that Democritus' vision gained empirical footing. The irony is rich. The same theory, scorned for lacking observable evidence in antiquity, became foundational to modern chemistry, yet Democritus himself had argued that truth often lies beyond human senses. He wrote, "By convention there is sweet, by convention bitter, but in reality only atoms and void." This distinction between perceived reality and underlying structure is a cornerstone of modern physics, from quantum mechanics to particle accelerators. Perhaps most poignant is how Democritus' insights emerged purely from reason, without microscopes or spectrometers. His methodology, combining logic with intuitive leaps, foreshadowed the theoretical physics of Einstein and Feynman. Today, we celebrate him as the father of atomic theory, but his legacy runs deeper. He represents humanity's enduring capacity to envision truths long before technology can confirm them, proving that sometimes the most advanced science begins not in a lab, but in the quiet moments when a thinker dares to see the unseen. Centuries before Europe saw its first canon, Chinese alchemists experimenting with saltpeter mixtures stumbled upon a discovery that would reshape history: gunpowder. By the 9th century Tang dynasty, these early formulas weren't just fireworks, they were being weaponized in terrifying new ways. Among the most devastating was the flying fire, a handheld bamboo tube that sprayed continuous flames using a gunpowder-fueled pump system, essentially the world's first flamethrower. Song Dynasty military manuals describe battalions deploying these against Mongol cavalry, creating walls of fire that melted armor and scattered horses in panic. But the real innovation came when engineers realized confined explosions could propel objects. By the 11th century, thunderclap bombs, ceramic shells packed with shrapnel and gunpowder, were raining down on enemies, their concussive blasts and iron fragments foreshadowing modern grenades. The leap from incendiary devices to true firearms came through gradual refinement. Early fire lances combined bamboo tubes with spearheads, initially designed to blast flame at close range. But as powder mixtures became more stable, soldiers noticed pellets or arrows placed in the barrel would shoot forward with deadly force. This led to the eruptor, a metal-reinforced tube that could fire multiple projectiles in succession, a direct ancestor of the musket. By the 13th century, the Yuan dynasty was casting the first bronze cannons, like the heaven-shaking thunder crash bomb, which could demolish city gates with a single shot. What began as an alchemical curiosity had birthed a new era of ballistic warfare, where victory no longer depended solely on muscle or steel, but on chemistry and controlled explosions. What's astonishing isn't just their early adoption, but how rapidly Chinese engineers iterated on these designs. Ming Dynasty arsenals produced hundreds of thunder bombs, cluster munitions that scattered smaller explosives on impact, while multi-stage rockets called fire dragons achieved ranges exceeding 1 kilometer. Naval warfare saw gunpowder used in underwater mines and timed floating bombs, tactical innovations Europeans wouldn't match for centuries. Even psychological warfare advanced, with magic cannon deployed at night, their flashes and thunderous reports designed to shatter enemy morale long before lead found its mark. The global spread of these technologies reshaped civilizations. When Mongol invasions carried gunpowder westward in the 13th century, it triggered an arms race that would topple medieval castles and feudal systems alike. Yet the original Chinese designs often surpassed their imitations. While European cannons frequently exploded from poor metallurgy, surviving Ming-era barrels show advanced casting techniques that distributed stress evenly. Modern firearms owe their existence to these breakthroughs, from the grain size optimization that made powders burn consistently, to the rifling principles first tested in Chinese hoop-barreled guns. The next time you hear a bullet's crack or feel a rocket's roar, remember, those sounds first echoed across battlefields in China, where alchemists seeking immortality instead unlocked the chemistry of destruction and changed the nature of power forever. Rising from the scorching deserts of Persia, towering structures of baked brick and clay stand silent against the relentless sun. These aren't monuments or minarets, they're ancient air conditioners. Known as badgers or wind catchers, these ingenious towers have cooled homes and public spaces for over 3,000 years without a single watt of electricity. Picture a square or rectangular chimney stretching high above a building, its top split into multiple vertical openings facing prevailing winds. As hot desert air enters, it's funneled downward through shaded internal shafts, where it cools against subterranean water canals or the building's thick earthen walls. By the time the breeze reaches living spaces below, it's dropped in temperature by as much as 20 degrees Fahrenheit, a feat of passive cooling so effective it rivals modern HVAC systems in efficiency. The physics behind badgers is deceptively simple yet brilliantly optimized. Each tower acts like a natural convection engine, exploiting two universal principles: hot air rises and cool air sinks. Some designs even incorporate courtyards with pools or fountains, where evaporating water further chills incoming breezes before they circulate through the structure. More advanced versions use internal flaps to redirect airflow based on wind direction, while underground canal tunnels connect to natural aquifers, transforming the earth itself into a massive heat sink. The result, a self-regulating climate control system that consumes zero energy, emits no greenhouse gases, and requires minimal maintenance, something our power-hungry air conditioners still struggle to match. Modern engineers are only beginning to appreciate the sophistication of these ancient designs. Studies comparing badgers to conventional cooling systems show they can reduce indoor temperatures by 10 to 15 degrees Celsius in peak summer, comparable to many commercial HVAC units, while using a fraction of the energy. Architects in Iran's Yazd province, where temperatures regularly exceed 120 degrees Fahrenheit, still rely on wind catchers to keep historical buildings comfortable. Even more telling is their resurgence in sustainable architecture. The Masdar city development in Abu Dhabi incorporated badger-inspired towers to cut cooling energy demands by 55%, while London's Queen Elizabeth Olympic Park features a contemporary reinterpretation that harnesses the Thames breezes. What makes these structures truly revolutionary isn't just their functionality, but their philosophy. Where modern air conditioning fights nature, sealing buildings and burning energy to overpower outdoor conditions, badgers work with it, leveraging wind, water, and thermal mass in harmony. They represent a forgotten truth about technology. Sometimes the most advanced solutions aren't about complexity, but about aligning human ingenuity with natural laws. As climate change forces us to rethink energy-intensive cooling, these ancient towers stand as silent mentors, reminding us that the future of comfort might not lie in smarter machines, but in rediscovering the wisdom baked into the deserts millennia ago. Bouncing between the hands of Olmec players over 3,000 years ago, rubber balls weren't just toys, they were a technological marvel centuries ahead of their time. Long before Charles Goodyear patented vulcanization in 1839, Mesoamerican civilizations had already mastered the art of transforming sticky tree sap into durable, elastic spheres. The secret lay in a process so ingenious it still impresses materials scientists today. Indigenous innovators harvested latex from native rubber trees, then mixed it with juice from morning glory vines, a combination that, unbeknownst to them, triggered polymerization. The vine's sulfur-rich compounds acted as natural vulcanizing agents, strengthening the rubber's molecular bonds to create a material that could withstand intense impacts without cracking or losing shape. These weren't casual playground objects. Surviving rubber balls from Aztec and Mayan sites show meticulous craftsmanship, ranging from fist-sized spheres to heavy 10-pound orbs used in ceremonial bowl games. At El Manotti, a sacred Olmec spring, archaeologists discovered perfectly preserved rubber balls dating to 1600 BCE, some still retaining their bounce after millennia underwater. The precision mattered. The ball game, known as Alamalistli, was both sport and sacred ritual, with courts designed as symbolic portals to the underworld. Players used hips and elbows to keep the ball in constant motion, imitating the celestial dance of the sun and moon, a game so physically demanding that protective gear like padded belts and knee guards evolved alongside the balls themselves. Modern laboratories have reverse-engineered these ancient materials, revealing just how advanced they were. Tests show Olmec rubber could rebound to 80% of its original height, comparable to mid-20th century synthetic rubber. Even more impressive is its energy efficiency. The material absorbed and released kinetic energy with minimal loss, a property engineers now strive to replicate in high-performance athletic gear. Today's running shoes with energy-returning midsoles, the same principle that made a rubber ball soar across a Mayan court in 2000 BCE. The legacy of these innovations stretches far beyond sports. NASA has studied Olmec rubber compounds for potential use in shock-absorbing spacecraft components, while biomedical researchers explore their natural elasticity for prosthetic applications. Meanwhile, the ecological wisdom behind the process using locally sourced, sustainable materials inspires green chemistry movements seeking alternatives to petroleum-based synthetics. Those ancient rubber mixers could never have imagined their creations would one day influence space exploration or medical science, yet their intuitive understanding of material science echoes in labs worldwide. Perhaps the most humbling lesson lies in what the Olmec didn't do. Unlike later industrial processes that rely on toxic additives and high-energy refining, their rubber required no fossil fuels or synthetic chemicals, just careful observation of nature's recipes. In an age grappling with sustainability crises, these millennia-old balls bounce a provocative question. Could the most advanced material science sometimes look not to the future but to the past? The next time you catch a basketball or feel the spring in your sneakers, remember the physics of rebound was perfected long before modern arenas, in the humid lowlands where rubber trees whispered their secrets to those patient enough to listen. The Antikythera Mechanism wasn't the only celestial calculator to emerge from the ancient Greek world, just the one that survived. Scattered through crumbling manuscripts and fragmented histories lie whispers of even more sophisticated devices, their secrets lost to time. Take the legendary sphere of Archimedes, a device so advanced that Cicero described it with awe centuries after its creator's death. Unlike the compact Antikythera, this elaborate model reportedly recreated the entire cosmos in motion, with planets orbiting a central Earth in their correct speeds and directions. Some accounts claim it even simulated eclipses and planetary retrogrades that peculiar backward drift planets sometimes exhibit when observed from Earth. Imagine standing before a bronze and glass celestial sphere where Mars slowed, reversed course, then resumed its path, all driven by hidden gears and hydraulics. The precision would have required mathematical insights rivaling Ptolemy's centuries before his star charts, but the sphere's true genius might have been its universality. Where the Antikythera focused on predictions, Archimedes' creation allegedly illustrated cosmological principles, a teaching tool that made heavenly mechanics tangible. Roman general Marcellus supposedly kept two as war trophies after sacking Syracuse. One stayed in his family's temple, the other became a prized exhibit in Rome. The irony, these spheres were celebrated as art, their technical brilliance overshadowed by their beauty. Later philosophers like Lactantius dismissed them as mere toys, unaware they held the seeds of orbital mechanics. Only when Renaissance scientists like Copernicus and Kepler rediscovered elliptical orbits did the sphere's potential sophistication come into focus. Could its moving parts have modeled gravity's pull long before Newton? We'll never know. The last known version vanished in the sack of Rome, its inner workings lost forever. Less famous but equally intriguing are the portable sundials of the Hellenistic era. These weren't simple shadow casters, they were multi-layered, adjustable computers made of bronze. The Rhodes calendar, a 1st century device recovered from a shipwreck, contained over 30 interlocking gears to track lunar phases, zodiac signs, and even irregular Egyptian months. Another from Olbia featured interchangeable plates for different latitudes, allowing travelers to recalibrate it like a modern GPS. They shared the Antikythera's miniaturized complexity but served everyday needs, proving such technology wasn't confined to temples or philosophers' workshops. Even common soldiers might have carried them, their brass components glinting in Mediterranean sunlight as they calculated time across conquered lands. The darkest mystery isn't the devices we've found, but those we know existed only through passing references. Byzantine lexicons mention star-following chariots, wheeled mechanisms that tracked celestial movements across palace floors. Hero of Alexandria wrote of automated theaters where celestial gods danced in perfect sync with the real night sky, likely using gear trains similar to those in the Antikythera. And then there's Posidonius' meteoroscope, described as able to grasp the heavens' revolutions, perhaps an advanced theodolite for measuring stellar angles. These glimpses suggest an entire ecosystem of mechanical astronomy, now almost entirely erased. Why did such brilliance fade? The collapse of the Alexandrian library and Rome's decline certainly played roles, but deeper forces were at work. Ancient Greek science thrived where patronage and curiosity intersected in Syracuse's courts, Rhodes' observatories, Byzantium's workshops. As empires fractured, so did the networks sustaining high-precision engineering. What survived were texts describing devices too complex to rebuild from words alone, like trying to reconstruct a smartphone from a poet's description. The Antikythera's survival was a fluke, a shipwreck preserving what fires and wars erased elsewhere. Modern reconstructions hint at what we've lost. When British engineer Michael Wright built a replica of the Antikythera's proposed planetary mechanisms, he found unexpected subtleties: gears that compensated for elliptical orbits using pin and slot arrangements, a method not seen again until 14th century clockwork. If one device held such surprises, how many other mechanical secrets still lie buried? The answer may wait beneath Mediterranean waves or in forgotten manuscript margins, fragments of a science that saw the universe not just as numbers but as gears in motion. The tragedy isn't that these machines were extraordinary, it's that they might once have been ordinary, pieces of a technological landscape we're only beginning to imagine. Buried in the peat bogs of ancient Europe, tiny fragments of glass still gleam with undiminished brilliance after 2,000 years. These aren't just decorative trinkets, they're masterpieces of material science crafted by Celtic artisans whose understanding of chemistry rivals modern nanotechnology. The most striking examples come from sites like the Celtic oppidum of Manching, where beads display vibrant blues and reds untouched by time. What makes these colors so enduring? Electron microscopy reveals the secret. Embedded within the glass are copper and silver nanoparticles precisely engineered to interact with light. At scales of just 5 to 10 nanometers, thinner than a human hair is wide, these metal clusters scatter light in ways that create intense, unfading hues through a phenomenon we now call surface plasmon resonance. The process behind these beads defies expectations. Celtic glassmakers didn't have furnaces capable of the extreme temperatures we associate with modern glass production. Instead, they worked at relatively low heats, carefully controlling cooling rates to encourage nanoparticle formation. By adding metallic salts to molten glass, then reheating and quenching the mixture, they triggered the growth of these microscopic structures through a process called nucleation. Some beads even show gradient colors shifting from red to yellow, achieved by varying the oxidation state of copper particles within the glass matrix. This level of control suggests an empirical grasp of material properties that wouldn't be formally understood until the advent of electron microscopes in the 20th century. Beyond their technical brilliance, these beads wove themselves into the fabric of Celtic society. Torques and brooches adorned with such glass weren't mere jewelry. They served as status markers, spiritual talismans, and even proto-currency. The famous Snettisham Great Torque, with its intricate glass inlays, likely belonged to a ruler whose power was literally reflected in the play of light across its surface. Chemical analysis tells a fascinating trade story too beyond distribution across Europe. The presence of cobalt blue beads in Ireland made with Egyptian cobalt points to vast exchange networks. These weren't just pretty objects, they were the semiconductors of their day, carrying cultural information through their very structure. Modern material scientists are now decoding these ancient techniques for cutting-edge applications. The same plasmonic effects that give Celtic beads their vibrancy are being harnessed in medical diagnostics, where gold nanoparticles detect cancer biomarkers through color changes. Photovoltaic researchers study these antique glass formulations to improve light absorption in next-gen solar cells. Even more remarkably, Celtic glass's resistance to devitrification, the clouding that plagues modern glass over time, has inspired new durable coatings for spacecraft windows. Perhaps the most humbling realization is how these artisans achieved such precision without the language to describe it. Where we see nanoparticles and quantum dots, they saw the fire of the gods trapped in glass. Their methods, passed down through generations of trial and observation, created materials that outlasted empires. In those tiny beads lies a challenge to our assumptions about progress, proof that nanotechnology isn't a modern invention, but a rediscovery of what hands guided by patience and keen observation once accomplished. The Celts left no written treatises on material science, but their glass still speaks across millennia, glowing with secrets we're only now learning to hear. From the celestial gears of the Antikythera Mechanism to the nano-engineered glow of the Lycurgus cup, these 25 examples shatter the myth that ancient cultures were primitive. They weren't just ahead of their time, they were dancing on the edge of discoveries we'd later claim as our own. Think about it, the precision of Mayan astronomy rivaling modern software, Roman concrete healing itself like living tissue, or Baghdad's clay jars humming with the same electrochemical principles as your car battery. These weren't lucky guesses, they were flashes of brilliance often lost and rediscovered centuries later, like cosmic postcards from the past. But here's the haunting question lingering beneath these wonders. Were they predictions, coincidences, or fragments of knowledge we've since forgotten? Consider the Vimana texts. Were they poetic myths, or could they hint at aerial technologies erased by time? When Democritus envisioned atoms without microscopes, was it philosophy or a forgotten science? Even the Dendera carvings, sacred art to some, blueprints to others, remind us how thin the line between symbolism and engineering can be. History isn't just a timeline of progress, it's a palimpsest where older truths sometimes bleed through the surface. Maybe the most humbling lesson isn't about who knew what, but how knowledge itself evolves. Civilizations rise and fall, taking secrets with them. The Antikythera Mechanism's gears might have been common in Alexandrian workshops, just as heroes' automata could have been everyday temple wonders. What we call discoveries are often just recollections, scattered pieces waiting to be reassembled. So here's your turn to weigh in. Do these parallels reveal a lost golden age, or simply the universal spark of human curiosity? Drop your wildest theories below, and if you're hungry for more mysteries rewriting history, hit subscribe. The past isn't done surprising us yet.